All right. Hello, everybody. Thanks for joining up. So today is a big day for us. We get to start schemes. So we have worked our way through 65 pages of math. Um, that is a non-trivial accomplishment, and I'm very proud of us. And yeah, now we get to start schemes, which are kind of like the the generalization of a major class of things in algebraic geometry. Um, so it's like a geometric embedding, I guess, is one way to think about it. So um, I guess the lead-in that Vakil gives is that we've seen notions of geometric spaces like differentiable manifolds, and that we want to abstract this notion so that it can be generalized to other settings, like non-smooth varieties and arithmetic objects. And the key insight behind this generalization from the notion of a manifold to something that is a versatile notion of a geometric space is the following. We can understand a geometric space well by understanding the functions on the space. More precisely, we will understand it through the sheaf of functions on the space. If we are interested in differentiable manifolds, we will consider smooth functions. If we are interested in analytic manifolds, we will consider real analytic functions, and so on. Thus, we will define a scheme to be the following data. And this is a loose definition. So, a scheme is um, the set, which are points of the scheme. The topology, open sets, and then the structure sheaf, sheaf of algebraic functions. It's worth noting that this is a sheaf of rings. Um, so recall that a topological space with a sheaf of rings is called a ringed space. We will try to draw pictures throughout this section. Pictures can help develop geometric intuition, which can guide the algebraic development and eventually vice versa. Um, we will try to make all three notions as intuitive as possible for the set. In the key example of complex varieties, we will see that the points are the traditional points and tuples of complex numbers, plus some extra points that will be handy to have around. For the topology, we will require that the subset where an algebraic function vanishes must be closed, and require nothing else. This is the Zariski topology. For the sheaf of algebraic functions, the structure sheaf, we will expect that in the complex plane, rational functions should be algebraic on the open set consisting of points where the denominator doesn't vanish, and this will largely motivate our definition. So we're kind of moving back towards the Hartshorne definition of affine variety and ring
Hmm.
irregular functions and that way of viewing it. We've covered those in total generalization now, and we see that the ring of regular functions is in fact a sheaf of regular functions,
Right.
right? More
Yeah.
importantly, the structure sheaf. Um, and I guess that's something that Hartshorne kind of gets to in his second chapter. We've kind of moved backwards. Um,
Yeah.
so, as a first example, we have differentiable manifolds. So let X be a differentiable manifold. Um, It is a topological space with a sheaf of smooth functions C infinity on it. And really, C infinity is our structure sheaf. And we have observed that evaluation at a point at a point P and X gives a surjective map from the stock of the structure sheaf to the real numbers. So um, and I'm going to give this a name, such that curve phi is equal to the terms of functions vanishing at P is a maximal ideal mx comma P is maximal. We could define a differentiable real manifold as a topological space with a structure sheaf that would require that we have an open cover of X, such that on each open set, the ringed space is isomorphic to a ball around the origin in Rn. With this definition, the ball is the basic patch, and a general manifold is obtained by gluing these patches together. Admittedly, a great deal of geometry comes from how one chooses to patch the balls together. In the algebraic setting, the basic patch is an affine scheme, which we will discuss soon. In the definition of a manifold, there's an additional requirement that the topological space be Hausdorff and second countable to avoid pathologies. Schemes are often required to be separated to avoid essentially the same pathologies. You don't need to worry about that remark.
Yeah.
So he has a remark, which is that functions are determined by their values at points. This is an obvious statement, but won't be true for schemes in general. So not true for general schemes. We'll discuss this soon. Morphisms of manifolds. How can we describe maps of differentiable manifolds? There are certainly continuous maps, but which ones? We can pull back functions along continuous maps. Smooth functions pull back to smooth functions. More formally, we have the inverse image sheaf, which gives us a map from structure sheaf to structure sheaf, which is left adjoint to push forward. And so you can push forward and pull back smooth functions. Certainly given a map of differentiable manifolds, smooth functions pull back to smooth functions, it's less obvious that this is a sufficient condition for a continuous map to be smooth. So let's see. So they have an important exercise for those with a little bit of experience with manifolds. I've never worked with them,
Yeah,
at
me
least not
neither.
knowingly. Um, so let me go ahead and just Google the definition to make sure that I'm not going to misinterpret something.
All right.
So smooth, no, differentiable manifold. Um, a space. Every point has a neighborhood that looks like an open set in Rn. Okay. So definition. Manifold. A set such that there's a set, I'll call it M for manifold. For every P in M, there exists a neighborhood around P which is isomorphic to an open ball around P in Rn. So what this means is that like if we're just taking the real numbers as an example, because this they certainly satisfy this condition, if we pick a point out, then we get this other blob that's a neighborhood that we could contract to our standard open ball. Does that make sense?
Could you explain that again? I was writing stuff down.
Okay, if we have this point P,
Yeah.
then the manifold admits this open neighborhood of P
Oh, okay.
that is isomorphic to its representation in Rn as an open ball.
Okay. That makes sense.
And what this looks like is this is like locally Euclidean space. So geometry isn't curved.
Yeah.
Um, so now I can state a theorem. Um, let pi from x to y be a map of differentiable manifolds as topological spaces. Show that, or sorry, I guess I'm saying this as a theorem. Pi from x to y is smooth if, and there's two equivalent statements, smooth functions pull back to smooth functions, or equivalently, um, if pullback by pi gives a map from the structure sheaf on y to the pullback of the structure sheaf on x. Um, wait, that is the pullback, right?
I believe so.
I'm tired.
The book is sad.
Yeah.
Or no, it's not two
Um,
things. They're both the same thing.
yeah, I think it's. I just want to make sure that I'm not missing something. Dude, I need to like circle this in bright red. Dude, I know it's around here somewhere. Okay, it's push forward. Okay, this is the push forward.
Oh,
Um, and that this admits the pullback. So, want to show there exists phi. Did I already use phi? No. Oy to the push forward of x, which is equal to um, the structure sheaf on I inverse of y. So we're sending f and u to pi inverse of f, pi inverse of u. Yeah, this does seem pretty easy to prove.
hmm.
And I mean, is that not just it? Like, this is well defined.
Yeah, I think it is.
Like, I think maybe what we have to say is, well, pi inverse of f is equal to g um, on pi inverse of u, which is open in y, and since g is in c infinity on y, pi inverse f, pi inverse u is smooth. I'm pretty happy with that.
Yeah, that works.
Um, and I guess the existence of f and u is for every p. Well, I guess for every p, such that well, no, for every p in X, there exists u isomorphic to u prime, which is open in Rn. Let f comma u be such a pair for OXP. And I think that that covers the other part of the proof is existence of f and u. And then I think that we're done. A little out of order, but we're done. Um, I am actually just gonna move this around so that it's in the right order. Okay. Um, a very related theorem that we kind of sort of proved on accident with this yellow bit
Yeah.
is that morphisms of differentiable manifolds induce morphisms of stalks. And we're denoting this by pi sharp from OY comma Q to OX comma P. And this is done on the level of this line, right? We're
Hmm.
saying, okay, we can pick
Yeah.
out such pairs, we can map them over, and then this maps to some point in pi inverse of U.
Right.
Um, and then as a corollary that we will prove, pi star of the maximal ideal of y at q is contained in the maximal ideal at x of p. Um, and so to be very clear, what we're mapping over is the construction of this map is that, you know, let u, or I guess let q be in u, which is open, in y, which is isomorphic to u prime, in Rn. Um, then we can define f comma u for all f agreeing um, on u near q. And then the actual morphism is that um, f comma u gets mapped um, yeah, to pi inverse of f pi inverse of u. And I feel like this is all a pretty reasonable construction,
Yeah.
right? And so we're just taking one section of the stock, and mapping it over to another section of the associated stock.
Mhm.
Um, and so I'll actually even write that in. Stocks map to stocks. Well, so the maximal ideal is all of the functions which vanish. So pi sharp of vanishing at q um, is a map that gets sent to vanishing at p. So I guess this is really stocks at q, and this is stocks at p. So then basically vanishing at q gets maps by pi star to vanishing at p. And of course, this is a surjective map, um, but not necessarily injective, right? Hence, we have one-sided containment.
Mhm.
Um, so for proof, let f comma u be an my comma q. Um, then f of q is equal to 0 in y. Pi star of f comma u is equal to pi inverse of f pi inverse of u. But since this is, a map um, on the category of manifolds, since pi is smooth, pi inverse of f is equal to g in c infinity on x. Pi inverse of u is equal to w, which is open in x. And since GW is in the stock on X at P, um, G of P is I want to say that W is isomorphic um, to W prime in Rn, which is an open subset. Um, and so since W prime is open in Rn, it means that What I'm trying to get at is that we can't have moved or like shifted the structure so much that we don't have a vanishing within P or within W.
Mhm.
So like really at this point, trying to show that P maps to 0 by G in
Mhm.
OXP. Um, I'm actually not sure how to show that this ends up being a vanishing.
Is there a
Um,
way to make a commutative diagram in diagram chase?
no, not really. Because it's like it literally is just this. We're trying to say that
Ah.
functions that vanish at Q go to vanish at P.
Mhm.
Um, so we're taking functions which have an explicit vanishing on an open subset. We're sending them over to another thing that has a vanishing at P.
Hmm.
Um, oh, and I'm dumb. That's given. OXP guarantees vanishing. Didn't need that. Didn't need that. Oh, wait.
Hmm.
Did need that.
Hmm.
Yeah. OXP guarantees vanishing. Um, and I guess if I were to add anything, it would be that P is in W since pi of P equals Q by construction.
Mhm.
Okay. There we go. Um, have we talked about tangent and cotangent spaces yet?
Maybe.
Okay.
It
So
doesn't sound too familiar.
it's a really important, cool idea. So the tangent space um of a topological space and really a structure sheaf of X um, at P is the maximal ideal of X comma P mod the maximal ideal at squared. And this ends up being um, the germs of linear functions vanishing at P. Right? And so what this gives us is a ton of linear functions that go through the point P and evaluate to 0 and give us a tangent bundle around it, right?
Mhm.
And so this is the tangent space. And so as a remark, I'll maybe even call this a theorem, pi induces a map of tangent spaces um, that mxp mod mxp squared wedge sum gets sent to myq mod m squared yq wedge sum. Um, and I just kind of want to say what a wedge sum is. This is gluing at a point. So if you have two circles and you identify a base point on them, like x naught and x naught, and we call this S1 and this S1, then S1 wedge sum S1 is equal to their gluing at the base point.
Okay.
And so what we're saying is that we're gluing all of the pieces of the tangent bundle at the vanishing.
Mm-hmm.
Um, and so in the same way that we're able to induce things on stalks, we're able to induce things at tangent bundles. This is an algebraic topology notion, but it's nonetheless interesting.
Okay.
Um, Similarly, there's an inverse map that doesn't require the wedge sum, which is that myq mod m squared yq can naturally map without wedge sum to mxp m squared xp.
Okay.
And this is called the cotangent map. Again, kind of taking on the co because it is error reversing. Um, okay. Side remark, manifolds are covered by disks that are all isomorphic. This isn't true for schemes, even for complex smooth varieties. There are examples of two smooth complex curves, x and y, so that no non-empty open subset of x is isomorphic to a non-empty subset of y. There's a Riemann surface X that just kind of breaks things. Informally, this is because in Zariski topology on schemes, all non-empty open sets are huge and have more structure. So, this is kind of where all of our motivation with the Zariski topology comes back to be helpful because we're finally using it. um, yeah, so now we're going into section 3.2, the underlying set of affine schemes. Um, I need to blow my nose real quick. So
All right.
one moment. Okay. So for any ring A, we're going to define something called the spectrum of A. In this section, we will define it as a set, but we will soon endow it with a topology, and later with a sheaf of rings on it. Such an object is called an affine scheme. Later, spec A will denote the set along with the topology and a sheaf of functions, but for now, as there is no possibility of confusion, spec A will just be the set. So to define, to give it the formal definition, so for ring A, spec A is equal to the set of ideals I such that I is a prime ideal, i.e. is generated by prime elements, right? So in number rings, this is kind of a trivial definition. In polynomial rings, it's more interesting because you associate this to irreducible polynomials, right? And so really what we're saying is that spec A is the set of ideals generated by irreducible polynomials. Um, so set of prime ideals, ideals generated by irreducible polynomials. Um, the prime ideal P of A will be considered as an element of spec A, will be denoted by an equivalence class. So P is an I, helps avoid confusion. Um, and then is an oh, or sorry, this isn't of I, this is of spec A. Spec A. Element of um sorry. Okay, hold on. I misread that. So
Hmm.
P, which is a prime ideal of A, when considered as P, which is an element of spec A, will be denoted by class P. Um, elements A and A um, are functions on spec A. Um, and their value at the point P will be a mod P. So keeping track, this is a ring element. This is a prime ideal. This is a ring element, mod ring element.
Awesome.
So a function can take values in different rings at different points. So for example, the function 5 on spec Z takes the value 1 mod 2 at the ideal generated by 2 and 2 mod 3 at 3. So this is an example of number rings, but basically
Hmm.
taking different prime ideals from spec Z and evaluating ring elements on them comes by this modular
Yeah.
thing.
Okay.
Um, so I don't know. I think for this section, this is kind of one of the less intuitive things that we've covered. So if there ever is like an example or a proof that we're doing that doesn't make sense in terms of how you would actually evaluate it to a number or a polynomial or something,
Hmm.
just let me know and like we can kind of break it down. I need to blow my nose again. Okay. And so Vakil gives us this clarifying statement. I hope it's a clarifying statement. An element A of the ring line in a prime ideal P translates to a function A that is zero at the point P. So an element A in A line in the prime ideal P translates directly um, to a function um, A, which is 0 at P in spec A. Right, so this is kind of the same idea as like if you have an element of an ideal, then like when we talked about Grosvenor basis stuff way forever ago. You know, if you have F in some ideal generated by like F1, F2, F3, right?
Yeah.
Then if you divide F1 by this set, then F reduces exactly to 0 by F1, F2, F3. Because it's possible to show that the operation of modular arithmetic on polynomials or any kind of ring that's a Euclidean domain is actually the process of Euclidean division, um,
Yeah.
which is best seen by the whole Grosvenor basis thing. Um,
Right.
but that's a talk for maybe a different time, once I know more about Grosvenor bases, which admittedly, knowledge is limited.
Hmm.
Um,
This is making decent amount of sense.
yeah.
Like it's really similar to our stuff over the summer.
Yeah, I mean, we're definitely getting like there will end up being more Galois group stuff.
Oh,
Maybe
perfect.
not soon, but there's
Yeah.
like whole sections of algebraic geometry that are all Galois groups.
Oh, awesome.
Um, and that section is called arithmetic algebraic geometry. And it's a kind that I'm particularly interested in because that's where elliptic curves kind of live.
Oh, okay.
Um, and so I actually, this is a total aside, but I just got this great book on the arithmetic of elliptic curves by Silverman.
Hmm.
And so I'm thinking once I figure out what my schedule looks like in the spring, and once we get through a little bit more algebraic geometry, I'm thinking about doing some stuff on elliptic curves. The main thing for me is I really want to get through probably the first 10 chapters of this before I'll feel like I'm ready. Um, I don't know, there's a pretty real amount that I don't know. So I'm just kind of trying to like get as broad of a base as possible, but not overstep in stuff that like I just won't understand.
Right. Okay.
Um, but yeah, so we're going to use these phrases interchangeably. So take note that this is like the correspondence.
Yeah.
Notice that if you add or multiply two functions, you add or multiply their values at all points. This is a translation of a fact that A to A mod P is a ring morphism. These translations are important. Make sure that you are very comfortable with them. They should become second nature.
Hmm.
So, if A is generated over a base field or a base ring, um, those generating elements are called coordinates, and we will be able to later interpret them as restrictions of coordinates on R space.
All right.
Um, so, so if A is over a base ring like a polynomial ring A, um, with generators x1 through xr. X1 to xr are coordinates on our space. So, kind of the whole thing that we're doing in this section, I think, is that we are building up a big dictionary between algebra and geometry. Um, and so we're going to kind of take all of the things that we are familiar with in abstract algebra and using the spectrum of a ring, translate them to geometric ideas that allow us to make actual geometric constructions for the first time since starting, a whole series on algebraic geometry. Um, I really would like this light to turn on. Dude. Okay, there we go. That's awesome. All right, now I can see. Um, in next chapter, not section, chapter, we will interpret functions on spec A as global sections of the structure sheaf, i.e. as functions on a ringed space. We repeat a caution of what we will call functions and others may call regular functions. We will later define rational functions. But yeah, basically function means regular function. Um, okay, we now give some examples of spectrums. So example, the complex affine line. So consider A1 over C, which is equal to spec of C over X. Let's find the prime ideals of C over X. So this is prime ideals of C over X. Um, so as C over X is an integral domain, 0 is prime. So is X minus A. Um, and so we kind of get this inclusion mapping of 0 to ideals of the form X minus A to C over X to evaluation at a point by F gets mapped to F at A, which maps back to 0. Um, and there are no other prime ideals. And this is basically by the fundamental theorem of algebra that all functions over the complex plane factor into x minus a things. And so for an ideal to be prime, it should be generated by some x minus a.
Right.
Um, and so there's a picture um, that Vakil draws.
Hmm.
So at points 0, 1, I guess he gives it a bit more space. 0, 1, a question mark. Um, we have, so if this is 0, 1, a. In C, we have maximal ideals x, x minus 1, x minus a contained in C over x. And then on this line, we have all of the prime ideals. And this is kind of the algebraic perspective. And then the geometric perspective is that this is the spectrum element of the ideal. And these correspond by modular relation to points of C, and the collection of all such points are the points of A1C, which are spec C over X. Um, and so it's kind of cool that like our construction of affine space over an algebraic closure is really just the spectrum of its polynomial ring. Like there is
Mm.
um this thing that just kind of works nicely.
Yep.
Um, and yeah, so this is the geometric perspective. Um, there is one traditional point for each complex number plus one extra bonus point, 0. Um, we can mostly picture the affine line of C as C. The point x minus a will reasonably associate to a and c. But where should we picture the zero ideal? The best way of thinking about it is somewhat zen. It is somewhere on the complex line, but nowhere in particular, because the zero ideal is contained in all of these other prime ideals. We will somehow associate it with this line passing through all other points. This new point, 0, is the generic point of the line.
Mm.
Generic point of A1C. It is generically on the line, but you can't pin it down any further than that. It is not at all um, any particular point. It's near every point. It's near everything, located nowhere precisely. This feels like the theology of the Trinity. Um, we will place it far to the right for lack of anywhere better to put it. You will notice that we sketch A1C as a real one-dimensional, even though C is not so. This is to later remind ourselves that this will be a one-dimensional space where dimensions are defined in an algebraic sense rather than in a complex plane geometry sense. To give you some feeling for this space, we make some statements that are currently undefined but suggestive. So the functions on A1C are polynomials. Um, so f of x is equal to x squared minus 3x plus 1 um, is a value. No, is a function. Um, let's see. Um, what is its value at the spectrum element ideal generated by x minus 1? Um, which we think of as the point 1 in C. Um, well, there's two kind of ways to do this. We can do x squared minus 3x plus 1 mod x minus 1. Or we can do f of 1.
Why are we able to do f of 1?
Because this corresponds to the point 1
Oh, okay.
in C. And I think as just a good example, let's do so x squared minus 3x plus 1 reduces by x minus 1 um, to be x squared minus 3x plus 1 minus x times x minus 1. Well, we know that x squared goes off, and then we get negative 3x plus 2. So then we'll reduce negative 3x plus 2 by x minus 1. We'll get negative 3x plus 2 plus 3 times x minus 1, um, which is equal to 2
-1.
minus 3 is equal to negative 1.
And then f of 1 is also negative.
Huh? Yeah, and
And
so
then
then
f of 1.
f of 1 is equal to 1 squared minus 3 plus 1 is equal to negative 1.
Interesting.
And so this is really interesting that
Yeah.
like the Euclidean division algorithm of polynomials lines up explicitly with evaluating points from the spectrum on functions.
Right.
So um, what is f of x at the zero ideal? It's actually just f of x because this is the whole affine line.
Mm-hmm.
Um, More complicated example. Let's take a rational function. G of x is equal to x minus 3 cubed divided by x minus 2. Um, we want to be able to say that g of x has a triple zero at 3 and a single pole at 2. We will be able to do this after chapter 13. Okay, never mind. Don't consider this.
Okay.
Um, yeah, way to help.
Hmm.
So now we'll consider affine line over K, which is algebraically closed. So A1K is equal to the spectrum of K over X. Um, this is the affine line over K. Um, we will use the same picture of the affine line. It looks like they look suspiciously the same because the smallest algebraic closure of non-finite fields is the complex numbers, and so any finite field um, looks like 1, 2, 3, 0. Um, Spec Z. So this will look a lot like the affine line over the closure of K. So they form a unique factorization domain with a division algorithm. Prime ideals are 0 and P, where P is prime. Oh, sorry, this is spec Z. The other one, this one looks like spec C over X. Yeah. So, 100 is a function on spec z. Its value at 3 is equal to 100 mod 3, which is congruent to 1 mod 3. Its value at 2 is equal to 0 mod 2. Um, or at 2. And at 5 is 0 mod 2. And so we want to say that 100 has a double pole. Do you know what a pole is?
No.
Okay, it's basically like a zero. Like in the
Okay.
context of complex analysis, if you have a function f of x and g of x, and maybe this function is h of x is equal to this, then the
Okay.
poles of h of x are x in C such that g of x is equal to 0. And it's
Oh,
where
okay,
you
that makes
induce a
sense.
division by 0.
So it's
Um,
either so it's just a discontinuity.
yeah, it's like a special in the context of complex analysis, what it looks like is like if you have a pole like here, then it
Yeah.
means that your function goes off to infinity in an asymptotic way.
Okay.
Um, and so what happens is that if you have a closed contour C around this, and you set a direction and you decide that you want to integrate the action of the function on the contour, then the integral, the path integral with respect to C of f of x dx is equal to 2 pi I of the residue at, if we're
Oh, okay.
calling this point x naught, residue of x naught of f of x.
Oh, okay.
And then if no such pole exists, then this contour integral is 0.
All right.
Um, It's a little outside of the scope of what we're doing, I think, but
Right.
basically we want to show 100 has a double pole because it has this double zero at 2. Um,
Hmm.
has a double pole at oh, sorry, not 100. We want to show that 27 over 4. I was gonna say
Why
has a double
27 over
pole.
4?
Well, because this wouldn't be a pole at 0. It has a double zero at 5. So
Okay.
this is a double zero, and it also has a double zero at 2, right? Because 5 twice is 25, 2
Yeah.
twice is 4, 25 times 4 is 100.
Hmm.
We want to say that 2704 over 4 has a double pole at 2, um,
I'm still confused on
because
where we're getting 27.
27 doesn't matter. I guess the idea is that it's prime,
Oh,
right?
okay.
So 27 has a 0 at, or no, 27 isn't prime.
Didn't
9,
it?
I didn't
That's
mean
9 times
27.
3.
Yeah, so it's 3 squared times 3. So 3 cubed. Yeah. So it has a triple zero at 3. Um And so basically its value at 5 is 27 times 4 inverse mod 5. And so 4 inverse, maybe we should do some number theory stuff, but basically 4 inverse is if you have a prime p that you're modding out by, you do
Yeah.
the extended Euclidean algorithm. But
Oh, okay.
also if it's like if you have just as a general rule some or I guess p plus or minus 1
Mm-hmm.
mod p is congruent to plus or minus 1 respectively,
Okay.
right? And so in this case 4 mod p
Mm-hmm.
is congruent to 4, 4 inverse is congruent to minus 1.
Okay.
So this is congruent to 27 mod 5, which is 2 times negative 1 mod 5. But this is
Wouldn't
congruent to 3 mod 5.
uh,
And if this does not make sense, please ask, because modular arithmetic is weird until you see it once, and then it's like, oh, that was easy.
no, it's making sense.
Okay. Um, yeah. So it has a double pole at 2 because when we evaluate, so 27 times 4 inverse mod 2, we get some weird things happening. We get that, namely, the GCD of 4 and 2 is 2, not 1. And so then I don't think that there's a multiplicative inverse assigned here,
Right.
right? So 4 inverse need not exist. Um, because if we were to reduce 4 mod 2, this is equal to 0. And so what we would be saying would be that 0 inverse mod 2. And that makes no sense.
Right.
There is no such thing, I guess. Um, hence double pole. I just want to check, what time do you have to go today?
I mean, whenever, just earlier the better, because I'll be spending it with my family.
Okay. Then let me see where we are. Yeah. So there's quite a bit in this section specifically.
All right.
I think that this section is really interesting, so I could keep going for a while. But if you want to spend time with your family, maybe I'll just keep going. You can hop off whenever you want to and watch the recording later.
Yeah, I got you. I'll probably hop off now, just kind of go. I think my dad's making breakfast at the moment.
Okay, cool. Well, have fun with your family and check
Thank
out
you.
the recording later today.
Sounds great. I'll see you, Tim.
See you tomorrow.
All right. Bye.
Okay. Silly but important examples and the German word for bacon. The set spec K, where K is any field, is boring. 1 point, spec 0, where 0 is the zero ring, is the empty set and has 0 prime ideals. What is the German word for bacon? Hold on. What is the German word for bacon? Oh, spec. That's really funny. Okay. Um, so spec equals the set containing only the zero ideal and German for bacon. Um, small schemes. So consider spec k over epsilon mod epsilon squared. Um, so this is the ring of dual numbers. It turns out to be quite useful. Epsilon should be a very small number, so small that its square is 0. Although it itself is not 0, it is a non-zero function whose value at all points is 0. Whose value at all points is 0. Thus, given our first example, functions not being determined by their values at points. And so prime ideals look like subsets of this which are generated by things that are irreducible. I need to look this up. I'm confused. So every prime ideal of dual numbers must contain the ideal generated by epsilon. And so this is, I think, just equal to the ideal generated by epsilon. It's helpful to think of spec A as an infinitesimal thickening of a point. Hmm. Okay. And then our second example is a little bit more familiar. So spec k over x mod the ideal generated by x. We will see this again repeatedly starting in a little while. We will think of it later as a shred of a particularly nice smooth curve. Um, well, this should be. I feel like this should be. Oh, wait, it's not mod, it's localized. localized at x. Okay, well now I'm even more confused. So I guess x represents 0. And so we're localizing things at the origin. So like k over x times a constant. And I guess it's a non-zero constant. And so these are this is the localization, by the way. And it's times the inverse of a non-zero constant. So we want the prime ideals of k over x. And so such prime ideals contain no polynomial with non-zero constant terms. And so basically any prime ideal has to be contained within x. And so this looks like the zero ideal and x. Okay. Okay. I'm not sure. Hmm. Okay, I'm a little more familiar with the next example, so I'm just going to move on to that. So the affine line over R is equal to spec R over X. Um, and what I'll show is that it's 0 x minus a, and then x squared plus ax plus b. And this is basically proof sketch. It's that any degree 3 polynomial um, shouldn't add roots that are unobtainable. I think. Because, like, if we have, like, pi x squared mod x minus 1, for example. Like, this is a dumb example, but, like, pi x squared reduces to pi x squared minus pi x plus pi. Um, this goes to pi x, and then pi x reduces by x minus 1, pi x minus pi x minus 1, which reduces to pi. Um, so like even for transcendentals, I guess maybe this isn't even the right argument, but like I know it has to do with irreducibility. I think it's something along the lines of degree 3 polynomials become reducible, but maybe not in R, right? Like consider x to the fifth plus 1. And let's evaluate, you know, x to the 11th minus 3x plus 2 mod x to the 5th plus 1. Well, f reduces minus x to the 6th times x to the 5th plus 1 um, to be minus 3x plus 2 minus x to the 6th. And then we'll call this h1. H1 reduces plus x times x to the 5th plus 1, which is equal to negative 2x plus 2, which is not in R. So, like, I guess maybe it's that higher order polynomials don't mod to they don't mod to points in the ring. Best guess. Dag 3 plus polynomials don't mod to R. So they're not really like interpretable. Yeah. So I don't. Why are those the only prime ideals of Rx? I guess it's that. So I was right when I said every irreducible polynomial in R over X has degree 1 or 2. Okay. I'm a little more happy with that. Um, okay. So we have the points that we would normally expect to see on the real line corresponding to real numbers, the generic point 0, and new points which we may interpret as conjugate pairs of complex numbers, the roots of the quadratic. This last type of point should be seen more as akin to the real numbers than the generic point. You can picture A1R as the complex plane folded along the real axis. But the key point is that Galois conjugate points such as I and minus I are considered glued. Well, let's explore functions in this space. So consider f of x is equal to x cubed minus 1 at x minus 2. Um, this is 7 because it's 8 minus 1 at x squared plus 1. We get x cubed minus 1 about x squared plus 1 is minus 1 minus x times x squared plus 1, which is minus x minus 1, um, which corresponds to minus I minus 1. Oh, so up here, this is minus 2I, and it's not in R, and that's why. Ah, that makes so much sense. One moral of this example is that we can work over a non-algebraically closed field if we wish. It's more complicated, but we can recover much of the information we care about because R isn't algebraically closed. There we go. That that was the missing piece for all of it. Um okay. Um for an exercise, describe the set A1Q. A1Q. Um this is spec Q over X, which is the prime ideals of Q over X. Something is irreducible over Q if it's irreducible over Z. So that's it's not the Eisenstein criterion. It's one of those algebra 2 criteria. Well, F in Q over X is irreducible. No, was it that it was reducible over Q? It was reducible over Q if reducible over Z. And is that an if and only if? If it is, then we get irreducible over Z implies irreducible over Q. Um, well, so now we're missing square roots of numbers, right? So now we're missing, like, now we don't have x squared plus 1 evaluating, or that's a bad example, x squared minus 2. Um, um, so now we have, Yeah. Yeah, so we end up getting like all kinds of prime degrees of polynomials. So it's basically just yeah, f such that f irreducible in Q. But like I guess the idea is you could have, a degree 3 polynomial that's irreducible now. Like x cubed minus 2. Or like any of the cyclotomic polynomials. Um, and so on for prime degree f in q or x. Yeah. Um, the next example is the affine line over FP. So over your finite field is spec FP over X. Um, so the prime ideals are of the form 0 or f of x, where f of x is irreducible of any degree. They correspond to sets of Galois conjugates in FP. Spec FP has p points corresponding to the elements of FP, but also infinitely more. This makes the space much richer than simply p points. For example, a polynomial f of x is not determined by its values at the p elements of FP. It's determined by its values at the points of spec FP. You should think about this even if you are a geometric person. This intuition will later show up in geometric situations. So I guess let's just take for an example spec z7 over x. Well, let's take squared minus 3x plus 6 at 3x minus 7. No, 3x minus, let's do 1. So this is 3 inverse. We're evaluating this at 3 inverse mod 7. Mod 7, we would do 7 is equal to 2 times 3 plus 1. 3 is equal to 3 times 1 plus 0. So 1 is equal to 2 times 3 plus 7. So this would be -2. So 1 is equal to 7 minus 2 times 3. And so 5. So 5. There we go. So we're evaluating this at 5 is going to give 25 minus 15 plus 6 mod 7. 16 mod 7 is 2. Or equivalently, x squared minus 3x plus 6 reduces by 3x minus 1 to x squared minus 3x plus 6 minus 5 times, or I guess 5x times 3x minus 1. And this is equal, and all this is mod 7. Taking for granted that we can cancel out this bit with this bit. This is equal to negative 3x plus 5x plus 6 mod 7, which is equal to 2x plus 6. So we're staying clear. And then 2x plus 6 reduces by 3x minus 1. 2x plus 6 minus 5 times 2. So minus 10. 3x minus 1. Because 30x mod 7 is negative 2, which is 5. Yeah, that makes sense. Is equal to 6 plus 10 mod 7 is 3 plus 3, which is congruent to 2 mod 7. So yes, we do get the same thing. So this is a very interesting way to approach it, and this is a very interesting intersection of like modular arithmetic stuff that I had never thought about this way with like the geometry of Spec. That's pretty cool. Um, yeah. Um, so now we arrive at a theorem. If K is a field, spec K over X is infinite. Um, so this is where we assume that there's a finite one, and this follows the proof of Euclid's proof for the infinitude of primes of Z. But basically, as a sketch, assume spec K over X equals N. Pick the largest two primes. Multiply them and add one. Yeah. So another example is that the affine plane over C is spec of CXY, Um, Now this is not a principal ideal domain. Um, and so it gets more complicated. We can name some prime ideals. Um, so we have 0. Um, then like x minus 2, x minus 3, or like x minus a, x minus b. And then, yeah, so x minus a, x minus b. Um, and then any product, power products, or just polynomials, x comma y or xy. And then basically we want to prove that this is all of the ideals that we can get. We want to show, oh, this was not, this is meant to be, we want to show that we can reduce any ideal to be generated by one of these kinds of generators using the Euclidean algorithm. Um, so now we can attempt to draw a picture of the affine plane. The maximal prime ideals correspond to the traditional points, x minus a, y minus b. We now have to visualize bonus points. 0 somehow lives behind all of the traditional points. Um, yeah. So the picture, the figure of the affine plane over C is if you have a point A comma B, then this is really the ideal generated by x minus a, y minus b. Um, 0 lives somewhere. And then if you have some ideal generated by f of x comma y that's irreducible, then you can evaluate it kind of as its own point set of points. Prime ideals are of dimension 0, so dim 0. Ideals of polynomials are dim 1, and then 0 is dimension 2. Um, Note that 2 maximal ideals correspond to the smallest points, right? So this is maximal ideals means smallest. Smaller ideals correspond to bigger points. So smaller ideal equals bigger point, and vice versa. All this is made precise with the Zariski topology in a way that we talked about in Hartshorne. Um, So, um, yeah, if we have kind of a larger set of polynomial coordinates, like A, C, N, spec C over x1 through xn, um, it just gets bad. Um, so all of the maximal ideals, these are kind of the most fruitful things to write out, are ideals generated by, x1 minus a1, x2 minus a2, xn minus an. Um, and then these are the only maximal ideals by Hilbert's weak Nullstellan shots. So Hilbert's weak Nullstellan shots. Um, if K is algebraically closed, then maximal ideals are like so. Boy, that really just feels like stating the thing that we needed to prove above. Um, and then Hilbert Strong, Nullstellan shots. Nullstellan shots. Is that if K is any field, um, every maximal ideal of K over generating set capital X has residue field which is a finite extension of K. In other words, any field extension of K that is finitely generated as a K algebra is necessarily also generated as a K vector space. This part, this equivalence is Zariski's lemma. So as a theorem that doesn't require Nullstellan shots, any integral domain A, which is a finite K algebra, must be a field. Um, and then proof is that we want to show for every x in A, non-zero, multiplying by x on the right from A to A is an isomorphism. Okay. That's weird. Just got a weird email about the hotel booking for the joint meetings. So, in combination with the Null-Stellan shots, this theorem gives that prime ideals of k over x 1 through xn with finite dimensional residue ring are the same as maximal ideals of k x1 through xn. So, in combo with Hilbert's no sun shots, prime ideals of k over x with finite dimensional residue ring are the same as maximal ideals of k over x. Um, so there are other prime ideals of like C3, the affine space. We have 0, which corresponds to a three-dimensional point. We have f of x, y, z, where f is irreducible. To this, we associate hypersurfaces. We have prime ideals of dimension 0, 2, and 3. But by this construction, we're missing dimension 1. Any such prime ideal is of the form just xy or yz or xz. There are a lot of one-dimensional prime ideals. It's not possible to classify them in a reasonable way. They correspond to things that we think of as irreducible curves. So, one-dimensional prime ideals correspond to irreducible curves. Thus, the answer to the purely algebraic question, what are the prime ideals of C over x, y, z, is fundamentally geometric. That's very interesting. So the fact that the points of the affine Q line correspond to maximal ideals of the ring Q over X, what we will soon call closed points, can be interpreted as points of Q closure where Galois conjugates are glued together. Extends to affine n space over Q. For example, in affine 2 space over Q, the square root of 2 is glued to the square root of 2, is glued to the negative square root of 2, to the negative square root of 2, but not positive negative. So, yeah, I think this is where I'll stop, and then we'll open up tomorrow with some more from here. So, thank you all for watching, and yeah, see you tomorrow.